Hello and welcome to this podcast on potential dividers. Probably going to be the first of three shorter podcasts because this is quite a big topic and I want to split it up a little bit. Potential dividers are part of a circuit which allows you to control the current or potential difference in parts of the circuit, something that a resistor can always do, and that's what's mentioned in these skills here. So using the advantages of a potential divider over series resistor, or particularly a variable resistor. So to review, you should be aware of what a parallel circuit is, particularly this final point, that in a parallel circuit, the potential difference across every branch will be the same as the potential difference across the supply. The potential difference across any branch is the same. And a variable resistor, because that's going to be important as a point of comparison, is this symbol here, which is placed in series in this particular example. And in the picture here, you have variable resistor where the electricity comes in here, goes through the coil before exiting, and you can adjust by moving this section backwards and forwards, which changes the length of coil that the electricity has to pass through. Variable resistors are useful, but they do have some disadvantages. One of those disadvantages is that the energy which is used up, which is lost as heat, so therefore if you increase the resistance, the potential difference across here is fine, so the potential difference across here goes down, so this is less energy here. That's not unuseful, that's what you intend it to do, but the problem is that there's going to be a maximum finite resistance and therefore a maximum percentage of the available energy that the variable resistor turns to heat, leaving some across the rest of the load. And if you want to, for example, completely turn off a light bulb, then a variable resistor is going to struggle to do that. The alternative, as we've seen, is the potential divider, and that's the advantage that one of the advantages that was being referred to. Let's start by looking at a very basic potential divider. A very basic potential divider consists of two resistors in series. Let's turn it on its side to make life easier to see. If we put in a couple of cables coming from either side of one of those resistors, those little circles at the end indicate that these are terminals. We can plug more circuitry into this, which would be parallel to that resistor, and by the laws of parallel circuits, will have the same potential difference across it. So as far as the rest of the circuit that you're adding in, and we'll look at an example later, is concerned, this is a power supply with a potential difference that is going to be a proportion of the greater power supply. So if this is 12 volts, this could be anywhere between 0 and 12 volts, depending on the ratio of the two resistances. So let's just get some terminology. V in is the terminal PD of the cell or of energy supply, and V out is the potential difference that's available to the secondary circuit that we're passing on. We'll label our two resistors, R1 and R2, and the potential across each of them is V1 and, in this case, V2. And V2, yes, is going to be the same as V out, but we'll come back to that. I, the current in the circuit, will equal the terminal PD divided by the total resistance of the circuit. The total resistance of the circuit is R1 plus R2, and the potential difference V1 and V2 across each of those resistors is given by V1 equals IR1 or V2 equals IR2, just the basic equation rearranged. Since V1 equals IR1, we can replace the current with V in over R to get V1 equals V in over R multiplied by R1, which is the same as this, which is the same as this. So in other words, V1, the potential difference across resistor 1 equals the resistance of resistor 1 divided by the total resistance multiplied by the terminal PD. Same for V2. And therefore, since V2 is V out, this is the equation that gives you the relationship between V out and V in. And it's a simple enough equation because it just says that the output voltage, the output potential difference, is the resistance of the resistor across which you're tapping divided by the total resistance, which makes you a percentage or a fraction of the input voltage. Let's show that in action. So, if we have a 12 volt supply and we have two 4 ohm resistors, then I think fairly logically, since we know that potential difference across V2 plus V1 will equal the total potential difference, then that's going to be half of 12, which is 6 volts. But just to show you the equation in action, R2 here is 4, R1 plus R2 is 4 plus 4, V in is 12, go through the maths, and you get 6 volts. If, on the other hand, we have a different ratio, we'll keep this one 4 ohms, make this one 2 ohms, then 4 over 6 is 4/6, which is 2/3, which is going to be 8 volts, 2/3 of 12 volts. So you can see how this output voltage will vary. And that's great, that's really useful. But let's look at some other applications in the next video.